Okay, so let's now look at another binding equilibrium example. So let's look at the dimerization of a molecule. Okay, so let's say we have a transcription factor that dimerizes. Yeah? Okay, so the first thing to do is that, okay, so there is a total concentration of A that we have. Well, that's the free concentration plus the dimer, but this is the total monomer concentration. So one dimer consists of two molecules of A, so there should be a 2 in front, okay? Important. And the rate of this reaction is described by K plus times A squared minus K minus times A2, the dimer concentration. Yeah? And we know now if you would do this experiment in the test tube, then the eventual state would be an equilibrium state. So in the equilibrium state, we know that the rate is related to the equilibrium concentrations, and that's going to be equal to 0. Now we can again define the dissociation constant for this case, and again it is a dissociation constant because it has unit concentration. And now what we can try to do, we can calculate what these equilibrium concentrations are using this relationship and the total concentration relationship for A. Okay, as we have done before in the previous example. So we know that at equilibrium the total concentration of A that I have is the concentration that I've added to my test tube, so A0, or you can call it A total, it's up to you. Equilibrium concentrations, like this, okay. This relation tells us that this is in fact equal divided by Kd, okay, and so now what we would like to do, we would like to calculate what the concentration of A is, right? But it looks a little bit more complicated than what we've seen before. So we cannot easily solve what AE is, okay? So because in fact we have this relationship now. And if we rewrite this a little bit, you see AE squared 1 over Kd plus AE minus A0 equals 0. So if you want to solve that for AE, you need to figure out how that works. And well, I'm not sure whether you know the equation. You don't need to know it by heart. I happen to know it by heart. So the solution of AE now, there will be two solutions. So let's say there's an AE solution. One of them is going to be minus 1 plus minus square root 1 squared minus 4 times 1 over Kd times 1 divided by 2 Kd. Right, and what I just wrote down is the solution to a polynomial equation. Because this thing has as a solution two solutions, minus b plus minus b squared minus 4 times ac divided by 2a. That is the general solution to this quadratic equation. Here we also have a quadratic equation. This is one of the solutions. So let's say this is the plus solution. So the alternative solution, denoted by prime, would be Okay, now only one of these solutions can be true. Okay, only one of these solutions can be physically realistic. So only one solution is physically realistic. So we have to figure out which one of them is not realistic. Well, if you look at this one, so we have the square root of 1 squared plus 4 times k 1 over kd times 1. So this is going to be a positive number, right? So the square root of a positive number is a positive number. So you get minus 1 minus a positive number. So this this numerator is going to be negative. And this is positive because kd is always a positive, has always a positive value. So this solution, right, is going to be smaller than 0. And this one, since you add something, it's going to be greater than 0. And in fact, this root is always greater than 1, so it's always going to be bigger than 0. So this solution, this one is not physically realistic. So that will be the solution. So the concentration of AE in equilibrium is going to be minus 1 plus the square root of 1 plus 4 divided by kd divided by 2 multiplied this whole thing by the kd. So you get kd times kd. So this is going to be the equilibrium concentration of A. Now the equilibrium concentration of the dimer is of course this thing squared divided by kd. So I have to take this root, so minus kd plus kd square root 1 plus 4 divided by kd divided by 2, I have to square that divided by kd. Okay, so this is another example of equilibrium concentration. So you see, you can always use the same trick. You use the definition of the dissociation constant because this relates equilibrium concentrations to each other, and you use this conservation equation for the total amount, and then we have two equations with two unknown equilibrium concentrations, right? So this is the total amount is related to the equilibrium concentrations, and that one is related to the equilibrium concentration. So we have two equations with two unknowns, and that you can solve, and then it then leads to a solution to the equilibrium concentration. Okay. So let's now continue. Let's say we have this dimer. This transcription factor dimer. Okay, so let's say we have A2, and let's now say that there is another molecule that can bind to it. Okay, so let's call that molecule B, and the dimer can bind to B. One of the monomers of A can bind to B, but also the other monomer of A can bind to B. So the right monomer of A dimer can bind to B, and the left monomer in A dimer can bind to B. And then each of them can bind to B again. Okay. Yeah, so if you think about this, say from a more physical perspective, so let's say this is the A dimer, and B is a square, then here the right P binds to the right, and here P binds to the left, and then in each case one circle is still unoccupied, and that also can be occupied by a square. Okay? So this is your A dimer, this is your B A square, A2 I mean, and here you have your A2B, and here you have your A2B2 complex, okay? So we can also analyze, of course, this problem. But now we have more reactions. So we have 1, 2, 3, 4 reactions. Now let's assume again that B is in excess. Okay? So that means that any binding of B to A dimers does not reduce the concentration of B. So that means the only conservation relationship we have to think about is the total amount of A that we have. Okay. Now the total amount of A that we have is of course the total amount of dimer that we have. So we have free dimer, this guy. We have dimer with the right monomer bound to B, and we have dimer with the left monomer bound to B, and we have dimers where both are bound to B. Now, we know now that there exists an equilibrium right, where V1, which is K1 plus times A2 times B minus K1 minus times A2B equals 0, and then we have equilibrium concentrations. There is also a V2, which is K2 plus times A2E times BE minus K minus by B E2E equals 0. And there's a third reaction, that is K3 plus, that starts from this complex, and then another B binds, K3 minus, times, how do I call that? B2 to B, E0, and these are equilibrium concentrations. And now there's a final reaction V4, and in this final that looks like this. Okay. So I have these 4 reactions in equilibrium. Each of these reaction rates is 0. And this leads to a definition of an equilibrium constant, which is A2E times BE divided by A2BE equals our first association constant. And here I have another one, which is A2E times BE divided by B2E, which is my second equilibrium constant. And the third reaction also has an equilibrium constant. It's my third equilibrium constant. And then I have a fourth equilibrium constant. And each of these equilibrium constants is associated with a certain ratio of these equilibrium concentrations. And in all cases they have the unit concentration. Right? So now what we want to do, we want to calculate what all these concentrations in equilibrium are, right? So that's also what we did in these other examples. That's typically the assignment if there is a set of equilibrium reactions, if there is a system that exists in equilibrium, we would like to calculate what these equilibrium concentrations are. Okay, so how to do that? So what we're going to look at this total. Right, we're going to look at this total in the equilibrium, under the equilibrium conditions. Yeah. Okay, so let's write this out again. So the total amount of A dimer that I have is free dimer plus dimer that has the right one bound, right? Okay, and so I can exploit K1 now, because this tells me that A2E times BE divided by K1 actually equals this concentration. The left one is related, the concentration where the left monomer is bound to B is related to the second dissociation constant. And now I have this one left, which is the end state. And the end state, I can either use this one or that one. So let's use K3. So this tells me that B A2 times E times BE divided by K3 equals that concentration. Now I'm almost there. The only thing that I have to get rid of is this term, because all the other terms are in terms of A2E. Okay, so I need to have an equation for the left one. That is in fact the one that I already used, so that's this one, right? So what you get A2E times BE squared multiplied by K2. So divided by the product of K2 and K3. Okay? So now I have this equation left, and the only unknown is the equilibrium concentration of A, because I have assumed B to be in excess. So I know that BE is in fact the total amount of B. Okay, the equilibrium concentration of B is the amount of B that exists in the system. So that's the amount of B that you add at time 0 when you would do an experiment. So in fact, I can use this equation now and solve for A to E. So A to E now is going to be equal to A2 total multiplied by 1 plus 1 BE divided by K1 BE divided by K2 plus BE squared divided by K2 times K3. So this is my concentration of the free A. Okay. So if I now want to calculate what the concentration of A2 BE is, right? Okay, well I know that is equal to A2E times BE divided by K1. I just calculated what A2E is, so this is going to be equal to, one thing I forgot, right? So the B concentration, of course, equal to B total, because we assume it to be in excess. Okay, so this is also now going to be B total, and A2 total times B total divided by K1, right, at 1 plus B total K1 plus B total divided by K2 plus B total squared divided by K2 times K3. Okay, so that is my second equilibrium concentration that I calculate. Yeah, now I need some more board. So let's just write this over here. So if I'm going to calculate now another concentration that I don't know, so this is, I want to know this equilibrium concentration, and what you will see is that it will be the total amount of dimer, B2 divided by K2, 1 over B2 divided by K1, plus B2 divided by K2, plus B2 squared divided by K2 times K3. And the final concentration that I want to know is the fully occupied state. That would be equal to this equation. So now I've calculated that this concentration in equilibrium, that concentration in equilibrium, this concentration in equilibrium, and that concentration in equilibrium. So I have all these equations now. So now I'm done. Okay? But there's one more thing to realize. So A2 is a homodimer. So it's composed out of identical monomers. So that means that the affinity that the left A molecule in the dimer has for B is the same as the affinity that the right dimer has for B. So that means that K1 is going to equal K2. No. Because A2 is composed out of two identical A molecules. And they are indistinguishable, they are the same. So in fact we can simplify everything. This 2 becomes a 1. 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 It's a 1. Becomes a 1. 1. 1. So that would be the final model of this binding reaction. Okay, I hope that's clear.